All right, so logarithmic functions are what we're going to talk about next. And what I want you to understand about logarithmic functions are that they are the inverses of exponential functions. So it's the inverse of an exponential. So there's a relationship between how you write a logarithmic statement and an exponential statement. They are tied together. So let's start with a log statement. So log, and then we'll put a b right down there. So that's a base b, and then we'll say of a is equal to x. All right, so that's a logarithmic statement. You've got a base, and then this is the exponent. Really, if we talk about an exponential statement, this could be rewritten exponentially as b to the x power equals a. Okay, so anything that's written as a logarithmic statement, an equation, could be rewritten as an exponential. And the same thing goes the other direction. If you've got an exponential statement, you can rewrite it as a logarithm using just some changes there. When we talk about exponentials, we talk about the base, like a base of a 2 or a base of a, on those examples that we had different bases. The base is the same as your log base. So when I read that, I say log base b. Might have a number down there like log base 2 or something like that. So that base is the same as the base when we talk about an exponential. So that's the relationship between logarithmic functions and exponential functions, is they are inverses of one another. And you can take a logarithmic statement and rewrite it as an exponential, or you can take an exponential and rewrite it as a log. And that's one of the first things that we're going to work on, is rewriting some logarithmic statements as exponentials, and then we'll write some exponentials as logarithmic statements. And those that concept is helpful when we get to solving equations. That sometimes it's easier to solve one that's written as a log statement than it is to solve it as an exponential, or sometimes it's easier to solve it as an exponential than as a log. So being able to manipulate the problem into something that's easier to do. Again, we talk about this, it seems like every week, every time we meet. Math, a lot of it is not necessarily doing a lot of new things. It's taking something that you get that looks new and make it look like something you already know how to do. So that's kind of what we can do with logarithmic functions and exponentials, is we can rewrite them into something that's a little easier to do one way or another. So that's the first thing we're going to talk about, is rewriting those. So we're going to write the log as an exponential. So we're going to take a log statement and turn it into an exponential statement. All right. First example, let's do log base 3 of 81 is equal to 4. So that's the logarithmic statement. We want to change that into an exponential statement. So it's log base b of 81 is equal to 4. That's how you read that. So if you read it the right way, it kind of tells you what's going on. Log base b, or base 3, says, oh, the base is a 3. And then whatever the log is equal to, that's going to always be the exponent. And then what does 3 to the 4th power equal? It equals 81. That's what's going on right in here. So it's always the base. This part goes with that part. This part goes with that part. And then this part goes with that part. Always. That's the way it's going to match up every single time. The base that the log is going to be the base of the exponential. Always. Never going to change as far as that goes. All right. Let's take another one. Let's say we had log base 2 of 8 is equal to 3. The base, again, it's log base 2, so that means the exponential has a base of a 2. It's equal to 3, so that means the exponent is 3. And then the exponential will be equal to what's inside of the log. What a logarithm is another way of writing an exponent, is what it ends up being here. Because look what this logarithm on example A is equal to. It's equal to 4, which is the exponent of the exponential. Same thing over here. You got a log base 2 of 8. That's equal to the exponent that it was as an exponential. Logarithms are exponents. And the whole, one of the reasons, not the whole reason, but one of the reasons that they exist is so that we could take really, really large numbers and make them manageable. Or we could take really, really tiny numbers and make them manageable. It's kind of like scientific notation was a way of taking bigger numbers that had a lot of digits and condensing it down to something that's a little bit more manageable. Logarithms can be used to do that as well. Exponentials, logarithms are all the same. They are inverses of one another, so they work together like that. Let's take another one here. Log base 3 of 1 over 27 is equal to -3. So we can have negative exponents. We know that those exist. We talked about those last week. We knew the rules that went with those, but here we're taking a logarithm. It's a base 3, so we know 3 is the base. The exponent is what the log is equal to, so it's -3 and 1 over 27. We're just taking that logarithm and rewriting it as an exponential, and then we're going to go the other direction in just a little bit. Okay. Say we had log base 6 of 1 is equal to 0. 6 to the 0 power is equal to 1. Notice that every one of these statements that I've written on the right here are true. Every one of the statements on the left are true too. That 6 to the 0 power is 1. Anything to the 0 power is 1. 3 to the -3 power is 1 over 27. If you check that with the calculator, these statements are true that we're getting there. Let's say we had get into what's called a common log, and common logs are dealing with a base that's understood. The whole idea of, we understand that if I write an x, that there's an understood 1 in front of that. With logarithms, if I write just the word log of 100 is equal to 2, well, there's a base right there that's understood to be there. They don't write it there. So if it's plain log like that, what to the second power is equal to 100? What squared is 100? 10, right? 10 to the second power. The common log, plain log, is log base 10. The reason that's an understood log base 10 is called a common log, is because we live in a base 10 number system, that everything is done by a place value holder that's a 10 exponential. Like the ones digit, if I had the number 365, that's really 3 times 10 squared plus 6 times 10 to the first plus 5 times 10 to the 0. I don't know why I did parentheses on that one. I guess. That's how our number system works that we live in. So when you talk about exponentials, a common exponent or exponential base is a base of a 10. That's why it's called a common log, is because we live in a base 10 number system. If you're talking about electronics or computers and things, binary code, you may have heard of that. Binary code is a base 2 number system. So if you're talking about electronics or computer systems, base 2 is important there. It's also something called hexadecimal, which is a base 6 number system that works with that sort of idea as well. But since we're dealing with common logarithms, we're a base 10. So if it just says plain log, understand that that's log base 10. They don't write it, but it's there. Okay, there's a 10 understood to be there. So make sure you know that. That's going to help us out later on. I did what I did. Let's do another common log. There's another common log. It's called natural log, and it uses ln. ln, and I'm just going to use a variable here because I don't know what e to the what power gives me 6. I'm going to use x there. What ln is called natural log. It's really log base e is another way of writing that. This is the way you'll see it all the time is natural log. But understand that natural log is just shorthand for log base e, with e being that exponential number that we used in continuous interest, 2.71 and some change. That's what e is. So if I rewrite this as an exponential, it'd be e to the x is equal to 6. That's how you rewrite that as an exponential. So natural logs have a base e. Natural log is base e. The common logs have their own button on your calculator. So on your graphing calculator down the left-hand side, you got a common log button, log base 10 there just beside the 7. That's log base 10. Beside the 4, that's ln. That's a natural log. That's log base e. They have their own button. Our graphing calculators now have a nice thing where we can change the base and use a different base thing, and we'll talk about that in just a little while about how to evaluate a log with the calculator. But the common logs, log base 10 and natural log, which is log base e, are right there, buttons on your calculator that you can use, and we'll talk about those as we go along here. So taking a logarithmic statement, rewriting it as an exponential is what we were doing there. So let's go the other direction, and let's rewrite each exponential as a log. Okay, so example G. Let's do 5 to the negative 3 equals 120 or 1 over 125. So we look at that and we decide, okay, it's an exponential because this side has exponents on it and it's got a base. What's the base on the left side? Base 5. So when we write our log, we'll write log and then base 5. Put a little 5 down there. And then we know that the logarithm should be equal to the exponent. What's the exponent in the exponential? It's negative 3. So it should be equal to negative 3. And then 1 over 125 is what we're taking that log base 5 of to get that statement. The base of the exponential is the base of the log. The exponent is what the logarithm is equal to every time, always, never changes. Okay, and then whatever's on the other side, that's what you're taking the log of. Those are always going to match up in that way. H. Let's say we had 3 to the third power is equal to 27. I'm going to rewrite that as a logarithm. That would be a log base 3, because that's 3, of 27 is equal to 3. Let's say we had 10 to the fourth power equals 10,000. Got a base of a 10, so it'd be common log 10,000 equal to 4. You can write the 10 down there, but you don't have to. You won't usually see the base 10 written on labs. I wouldn't count it wrong if you wrote it like that. That's fine with me. But understand that on the multiple choice portions of the Canvas quizzes or the final, you're not going to see that 10 written there. I'm just going to write log out of that. Okay. Let's see. Let's say e to the fourth power is equal to y. So e to the fourth power is equal to y. So I'm just throwing a variable in there. Remember, e is not a variable. E is a number. So it's got a base of e. So we know that's a common log of natural log of y is equal to 4. No, that the natural log is probably the most confusing one because it doesn't have anything, there, and it's a whole different thing. It's ln, natural log, and why the L's in the front, I don't know. I missed that day on math history class. So, all right, so taking a logarithmic or an exponential statement and rewriting it as a log, taking a logarithmic statement and rewriting it as an exponential. Not strenuous work there, but it's an important part because it can really help us when it comes to solving some equations. So we're going to kind of take that idea and morph it into solving some equations using that concept. Okay. So instructions are to solve, and let's say we had log base x of 16 over 9 is equal to 2. Well, that's an equation. It's got a logarithm in it, and a lot of times that makes it tough to deal with because it's a log base x, and so we don't even know what number the base is. But we do know, because we just talked about it, how I could rewrite a logarithmic statement as an exponential. If I rewrote this as x squared equal to 16 over 9, that problem makes a lot more sense. That's one that I've done something similar to before, that I could actually solve that problem. How would I get rid of the squared on the x? I'd take the square root, wouldn't I, of both sides. And anytime I take a square root in a problem, I got to put the plus or minus in front. Remember, that's important. So if I do that, that's x on that side. And what's the square root of 16? It's 4. What's the square root of 9? It's 3. So we solved that equation. It looked like Greek when we first saw it, but because we know we can rewrite it, it helped us in solving it. Sometimes rewriting it doesn't work and we need to do something else, but first kind of glance at something, think about rewriting it and see if it'll help. That case, it made it a problem like we've seen before. Again, it's that idea of mathematicians take things that we are kind of new to us and try to make them look like things we've done before. That's what we try to do. Take a problem like this: log base 2 of x is equal to 3. That's a tough problem. It looks, the x is inside of a logarithm, so that makes it tough to kind of figure out what's going on. But I do know that it's a logarithm, so I can rewrite it as an exponential, and maybe it makes more sense then. Well, the base is a log base 2, so that means it's 2 to the third power is equal to x. Oh, that turns out to be a pretty easy problem. Now, what's 2 to the third power? 8. X is equal to 8. We solved that equation just by using our rewriting property that we could do. Okay, just taking a logarithm and rewriting it as a exponential in these two cases. Okay. Let's go a little deeper here. Let's say we had log base 36 of the square root of 6 is equal to x. This one's a little tougher, but it's the idea here is that we may be able to manipulate this into an equation style that I could work. And if I look at that, I see, okay, I got a log, it's equal to x. Maybe if I take that and and set it up as an exponential. 36 to the x is equal to the square root of 6. So that square root was already in the problem, so I don't have to put plus or minus in it. Now, here's where what we talked about before break, where we could rewrite this as the same base, could help us solve this equation. What do I know about 36 in relation to 6? That it's actually 6 squared, right? And this goes back to last week with the rational exponents. 6 under a square root is also 6 to what power? What exponent? A square root becomes, we put the index there and the exponent there, 1/2 power. Now, what have I done? I've rewritten the problem with the same base on each side. So I've taken a logarithmic statement, turned it into an exponential, and then used those rules about exponents that I know. And then that 6 to the 2x is equal to 6 to the 1/2. And then I can solve that equation by dropping the bases. And that's 2x is equal to 1/2. If I divide by 2, 1/2 of a half is a 1/4. So taking a logarithmic statement and rewriting it as an exponential can help us solve some of these equations. Let's take another example. Log base 4 of x is equal to 5 over 2. Well, I don't know about much about that other than I can rewrite it as 4 to the 5 halves is equal to x. Base, exponent, what's it equal to? And then, hey, 4 raised to the 5 over 2 is just a number. All I got to do is work that out. 4 raised to the 5 over 2. 32. And I'm done. Because I could rewrite that as an exponential instead of as a logarithmic statement, it helped me solve that equation. Are they all going to be that simple? Absolutely not. But that is a definitely a valid strategy for looking at problems and saying, okay, can I rewrite this as an exponential? If I do, will it help me? Will it just work out really easy then if I do that? Let's do one more. Let's say we had log base square root of 7 of 49 is equal to x. This one just adds a few things in there. Okay, so here we have square root of 7 raised to the x power is equal to 49. So that's how we're rewriting this as an exponential. The base, the x is the exponent, and then whatever's inside of the log, that's what it's equal to. And then I'm going to manipulate that into 7. Okay, I know 49 is 7 squared. And I know the square root of 7 is 7 to the 1/2. So again, we're taking things, and we took a logarithm and rewrote it as an exponential. Well, that kind of triggers, hey, let's write everything as an exponent if we can. So we've got a square root. We're going to rewrite it as an exponent out of that. So here we got 7 to the 1/2 x is equal to 7 squared. The bases drop out. 1/2 x is equal to 2. Divide by 1/2. How many halves are there in the number 2? There are 4 of them. 1/2 is 1. Another 2 halves is 4 halves. And that's x equals 4. Okay. So taking a logarithmic statement and rewriting it as an exponential is definitely a good way to solve some of the logarithmic equations and be able to make them a much easier problem than if we tried to solve it while it had a log in it. All right. Now, the next thing that we're going to talk about in this section are the properties of logarithms. Okay, so we're going to spend a minute here talking about those properties and what they are and defining them, and then we'll start doing some examples to use them. So the properties of logarithms. All right, so properties of logarithms are related to the properties of exponents. Okay, so there's with exponents, we had the power property, which was when you had an exponent on the outside of the parentheses. So with logarithms, if you have a log, it doesn't matter what base the log is, these properties carry on for whatever base it is. So I'm going to use some variables here to define them, and then we'll get some examples of some actual stuff in it to work with. So let's use log base A of b to the x power. So that's our log that we're given. One of the properties, the power property, you don't have to know the names of them, is that if there's an exponent on the part you're taking the log of, you can bring that to the front and multiply. In exponent rule world, that was like having something where we had 3 squared to the 4th power. That exponent property said you did what with those 4 and the 2? You multiplied them. It's the same thing here, because remember, a logarithm is an exponent. So, and if there's an exponent on an exponent, then it's multiplication is the rule. Okay. So what we can do is we can take that power of that exponent and drop it down to the front, and take something that's an exponent and turn it into a multiplication problem, which multiplication problems are much easier to undo than exponent problems are. So that's kind of the idea here. So we're trying to take some things and make them into easier things to undo, because we're going to use these to help us solve equations eventually. Okay, so there's one of the properties of logarithms. Another property of logarithms is the product property. And with exponents, anytime you multiplied things together that had the same base, so like x squared times x to the 4th, what was the rule that you did with those exponents? If I multiplied x squared times x to the 4th, you add them up, okay? So with logarithms, if you have multiplication on the inside of the logarithm, that will turn into an addition problem. Log base a of x plus log base a of y. So we can take a multiplication that's happening into a log inside of a logarithm and split it apart into an addition problem. Okay, and addition again is easier to undo than multiplication is, right? It's a much easier operation. That's why we learn it so much earlier than we do multiplication in school, right? Now, so if we multiply, we turn it into addition. What happens if we divide? Well, the exponent rule was that if we had x to the 5th over x squared, what would you do with those exponents since the bases were the same? You would subtract them, be x to the 3rd. So same thing with the log. If you've got a division inside of the log, you can split that apart into log base a of x minus log base a of y. And it's always top minus bottom. X was on top, so it goes first. Y was on the bottom, so it goes second. It's always going to be in that order. Never going to change order there. Okay. So we have a power property, we have a product property, and a quotient property that we deal with here that helps us into manipulating a logarithm into a sum or a difference of logarithms, of several smaller logarithms. Okay. So what we're going to do is we're going to take some examples and we're going to expand the logarithm into a sum or a difference of several logs, or ever how many we need, just to make them each as simple as possible. Okay, so that's what our next examples are going to be. We're going to expand or write as a sum or a difference, and then we're going to go the other direction. We're going to take one that's already expanded and condense it down into one single logarithm, which is the expansion. You don't really use a whole lot in solving equations. Remember, everything that we're doing is to help us solve equations. So the expansion you don't use very much to solve equations, but the expansion really helps us learn the properties. Because the condensing is what we really will use to solve equations, that we will condense a logarithm statement down into one log, because one log is easier to get rid of than 14 of them. So we won't have that many, but the idea is that a single log is easier to undo than several. Okay, so we're going to learn the properties by expanding, and then we'll condense it, and that's the skill we're really going to use to solve some equations eventually with this stuff. So first set of examples, we're dealing with logarithmic properties. Expand each log into the sum slash difference of logs. Okay, so we're going to take one log that has a lot going on inside of it and split it apart and get it into smaller pieces. So letter P, example P. All right, so example P, let's take log base 7 of 3x, just 3x. We don't get too complicated on the first one. Make it easy. Well, what's going on between the 3 and the x on the inside? They're multiplying. So multiplication turns into addition. We're going to have log base 7 of 3 plus log base 7 of x. Multiplication turns into addition. Okay, it's just like the example. It's just got a number in it, a couple of numbers in it. Let's say we had log of x over 4. What's the base on that log? It's not written there. What's it going to be? 10. We understand that that's log base 10. I bring that up just so that you make sure you're remembering that, because it's going to come in play here not too long from now. So we got a division problem. Be log of x minus log of 4. And we've expanded it. We're taking logs, expanding them. This one just had, these two so far just had one property to deal with. Let's take one log base 3 of x to the 5th power. Well, that's an exponent on what's inside the log. There's nothing else going on there. So I can drop that down to the front and make it 5 times the log base 3 of x. Now let's start putting a few of them together. Okay? More than one property at a time. Okay? So let's take log base 4 of x squared y. Okay? So taking the log base 4 of x squared y. So what's going on inside of that log? Well, there are two pieces, right? There's an x squared and there's a y. What's going on between those two pieces? Their multiplication. So first step would be that it's log base 4 of x squared plus log base 4 of y. Okay? So the multiplication between the two pieces makes it an addition problem. Then we look at each piece of the addition problem and say, can I do anything else to it? Okay. So the first piece, we got log base 4 of x squared. It's got an exponent on it. Where can that exponent be moved to? Down to the front. Okay. That's going to be 2 log base 4 of x plus log base 4 of y. And that's all you can do to that one. There's nothing else you can do. After you've done several of these, you'll start doing more than one property at a time. You won't write out step by step as much. But you know, again, step by step's not bad. It just takes a little longer to do sometimes. Let's say we had example T, log base 3 of x cubed root of y squared. And I'm putting that in parentheses so it's clear what's the base of the log and what we're taking the log of. Your book or might not have parentheses around that. All right, so this one, when I see anytime I see a root in a problem, like here we got a cube root, I always automatically, before I go any further, I rewrite it as an exponent. So what would the exponent for that part turn into? Y to the what power? 2 over 3. So I rewrite it like that before I start expanding it, or I at least think of it that way. Don't think of it as a cube root of 3, cube root of y squared. Think of it as y to the 2/3 power. Okay, so you want to always think of things exponentially. All right, and then the next thing would be, okay, now I got two things in there. I got an x and I got a y to the 2/3. So they're multiplying together. So that means my problem is going to turn into log base 3 of x. And then the other piece is going to be log base 3 of y to the 2/3. But what's between them? What operation is between those two? Addition, because it was multiplication to begin with. Okay. Then I look at each individual piece and say, can I do anything else with that? So this x doesn't have an exponent, so I can't do anything to that. This y has an exponent. I can take it and drop it in the front to that power rule. I have log base 3 of x plus 2/3 log base 3 of y. And there we've expanded that logarithm as far as it will go. Log base 7 of x to the 3rd over y to the 5th. Well, big thing is it's a division problem, right? Because it's a big fraction. So if it's a division problem, what's it going to turn into? Subtraction problem. So the top minus the bottom. So log base 7 of x cubed minus log base 7 of y to the 5th. Then we look at each individual piece and say, can I do anything else to this one? Well, there's a 3 exponent. Where can it go? Down to the front. This one has a 5 exponent. It can go down to the front of it. So minus 5. And there we've expanded that as far as possible. So here we had a couple of properties. We had the power property and the quotient property all together. Let's go a little tougher. Let's say we had log base 2 of x y squared over w to the 3rd z. All right. So we got a lot going on with this one. It's got a lot of stuff inside of that log. So we want to take that and expand it. So it's a big division problem right now because of the fraction form. So I can split that apart into log base 2 of xy squared minus log base 2 of w to the 3rd z. So I'll start out by doing that. So that's step 1. And then I look at each of those pieces and say, can I split that apart or in any way or make it, move an exponent or anything? So the first piece, what's going on between the x and the y squared, they're multiplying, right? So that's going to become log base 2 of x plus log base 2 of y squared. I'm going to give myself a little bit more room there. Give myself enough room. And then this one, we got two things multiplied together as well. So we got log base 2 of w to the 3rd and log base 2 of z. Now, why did I put that in parentheses with the minus sign on the outside? What's that telling me that I'm doing? It's like distributed property. I'm subtracting both of those pieces, right? So when I finish this off and do my power rules there, I'm going to take this log base 2 of x plus 2 log base 2 of y minus 3 log base 2 of w minus log base 2 of z. So everybody that was in the denominator of the fraction has a minus sign in front of it. That's the key to think about here. Anybody that's in the numerator is positive. X and y squared, both of those logs that have those pieces, they're both positive. The w to the 3rd and the z, they were both in the denominator. Those logs both have negatives on them. So anything that's in the bottom is going to have a negative. Anything that's in the top should be a positive out of that. So that's always a good check to have at the end. Once you've done that, let's look at it and say, okay, if it was in the bottom to begin with, before I expanded it, then it should have a minus sign in front of it. If it doesn't, then I did something wrong. Let's go into the condensing version of this. Okay, so we're going to condense into a single log. So we're going to take some that are already like the final answer here, and we're going to put them back together into a single log is what we're going to do. So condense into a single logarithm. All right, so we'll start semi-easy. W. Log base 4 of x minus log base 4 of y. Real simple. It's a subtraction problem, so we know it turns into a division problem. Log base 4 front divided by back, x over y. You condensed it into a single logarithm. All right, so this one has 3 pieces. It's 3 log base 2 of x plus 4 log base 2 of y minus log base 2 of w. So we want to condense this down into one single log base 2. And you can do that in one step, or maybe take a couple of steps to do it to help us understand. Okay, so first thing that you should notice is there's numbers in the front. Those numbers in the front need to go back up as exponents. There's not a number in the front here for the w, so we just leave it that. And so that's going to be log base 2 of x squared plus log base 2 of y to the 4th minus log base 2 of w. So I'm just doing this one step at a time here so we can see where every piece comes from. Then I look left to right and see if I can simplify some stuff. So I've got an addition problem right here, which tells me that those 2 pieces do what together? They multiply. So I'm multiplying x squared times y to the 4th. Then I see I have a subtraction problem there. So I'm subtracting by log base 2 of w. That tells me, oh, then that means that that's a division problem. They're dividing by that w. So it's going to be log base 2 of x squared y to the 4th divided by w. And now we've got it down to a single logarithm. I am absolutely fine with you going, shorter steps, doing more than one property at a time. That's fine with me. I hope you get to where you can do that. If you're having trouble with that, practice is going to help get you to where you can do more than one property at a time. All right, let's look at example y. 4 log. Let's do natural log of r minus 5 natural log of x. So we see numbers in front. We know those are going to go up automatically. And we see a minus sign, which tells us this becomes what kind of problem? Comes a division problem, right? R to the 4th on top, x to the 5th on bottom. All right. let's take one that's got a few more things going on. Let's take a 1/3 log base 5 of x plus 2/3 log base 5 of y. Let's just start with that, and then we'll get one that's got a little bit more going too. All right, so numbers in front become exponents, right? So that's going to be log base 5 x to the 1/3 plus log base 5 y to the 2/3. Now, it's addition. So that tells us that it's multiplication, right? A little bit more in here. So that's going to be log base 5 of x to the 1/3 times y to the 2/3. And this is where this one can be a little bit more difficult, because look at the denominator on the fraction exponents. They're the same, right? So that means that this could be under the same root. What root would it be? The index would be a 3, right? The cubed root of x to the first power, y to what power? Second, yeah. And that would be the condensed version of that problem. So that's where that one can get confusing, is when you have those exponents with fractions and different exponent on those, but the same denominator out of that. That allows you to put them underneath the same root. If they had different denominators, this particular textbook and most mathematicians would just leave them with the exponent form, because if one of them had like a 1/5 power and the other one had a 2/3 power, they'd just leave them that way, because it's, doesn't really make it any better to put them together, because the denominators aren't the same. If the denominators are the same, then you put them into the same root, which works out real nice there. Okay. We went through the whole alphabet, so let's start doubling up letters. Let's do A. Let's take one that maybe log base 10, and see if we can work with that. So let's say we had log of x plus 3 log y minus 1/5 log z. Maybe that's what's going on. All right. So, same idea here. We got addition problem, and then a separate, subtraction thing. So, we think about the addition together. That's going to be multiplication, right? So that's going to be, but we got a power here. We got a 3 in the front, so that's going to go up. So these two are going to be log of x y to the 3rd, right? And then on the bottom, because that's a minus, we're going to have z to the 1/5. But the 1/5 power could be rewritten as what? The 5th root of z. I would accept either of those. This is probably the way you're going to see it in most textbooks, is with the 5th root. Because there are all these different exponents on this, that's why I kind of actually like this first, the one on the left, better. Just because you got all those letters and different exponents on those. If they all had a denominator of a 5, then hey, maybe I put it under the fifth root. But since they don't, I would have probably left it there. But this is the most common way that you'll see it in most textbooks, especially this one that we're using for the course. They tend to do it that way. All right. So condensing, that's going to come back in the next to the last section we talked about this evening when we're solving logarithmic equations. The condensing is going to help us be able to get rid of the logs all in one swoop instead of one at a time. Hey, last thing in this section is just evaluating a log with the calculator. So I want to show you how to do that, how to get your calculator to do different logs and work those out. So evaluate, this is the easiest part of the section, the easiest part of the night, with the calculator. If you can spell calculator, calculate for. All right, so easy when it's example where we're just got a common log, like example AB, log of 62, just a common log. Your calculator has a button for that common log. There on the left, right beside the number 7, you just hit log, and then we type in the number 62. That's the right number, isn't it? And we round that. I'm going to go 4 decimal places here because that's common place for this particular textbook, and your quizzes, I think, go 4 decimal places as well. So that's about, so I'm putting the approximation instead of an equal sign, 1.7924 out of that. So with a common log, we're just using those buttons. So if you had natural log of the number 10, your calculator has a button for natural log. It's right there beside the 4. You get natural log of 10. Here, 2.3026. Okay, so common logs, that's easy to, you just hit it and you don't have to go anywhere to find those. There are buttons right there on it. When you've got something that's a little bit more exotic, like a log base 2 of 15, and you can't evaluate that, 2 to a power, we don't know 2 to what power gives me 15. If it's 16, it'd be 2 to the 4th power. I could do that, but because it's 2 to the 2 to what power gives me 15 is what we're trying to find. It should be something less than 4 and bigger than 3. Now, here's how you can get a log base 2 with your graphing calculator. They've got really fancy with the programming that they've done. What you do is you hit the math button and press up to get down to the bottom of that list, and you're looking at option that says log base. And then it gives you this fancy looking thing that has a box for the base 2 and then 15. And it'll work that out for you. Okay, log base 2 of 15. So you're looking for this thing that's called log base, log base. Okay, on your calculator. It's under the math button. Math button, and then press the up arrow. It'll be down at the bottom of that list. Math button, and press the up arrow, get you there quicker for log base. And then you can type that in, gets the box for the base, and then the number. And we got 3.9069. Is that right? Yeah. Now, that's using the log base. Let's do another one using the log base, and then I'll show you what's called the change of base formula. In case your graphing calculator dies and you've got a scientific calculator, it'll do different bases too. It's just you got to be clever about it using this little change of base formula. So let's do log base 3 of 29. Okay, so I'm going to hit math, press the up arrow, get log base 3 of 29. So it should be a little bit more than 3 because 3 to the third power is 27. So 3.0650. 0650. Well, that's using log base to do that. There's a thing called the change of base formula. And I actually have seen this come up on the final exam. That's why I go over it. Is the change of base formula has come up on the final before. Doesn't do it every year, but they'll throw it in there every now and then. And it's really easy if you know it. So change of base formula is taking a logarithm that has a different base. It's not a common log base. So maybe it's log base 2 of a number, and let's do the number 12 out of that. You can do that with a common log by just doing the log base 10 of 12 divided by log base 10 of 2, or natural log of 12 divided by natural log of 2. The base always goes to the bottom. That's the way I remembered it this way. When I was going through college algebra in class, we didn't have the log base function on our graphing calculators. We had graphing calculators, but they wouldn't do near what you guys have access to now. So we had to know this, and the way that I remembered it is the base goes to the bottom. Okay, and what that allows you to do is just to do this problem using the buttons that are on your calculator instead of having to go to that menu and get that. If I do math and then log base, I want to show you that it's the same number, log base 2 of 12 and then log of 2. They're the exact same thing. If I did natural log of 12 divided by natural log of 2, it's all the same number. It works wonderfully. I will catch myself just, I guess, out of old habits using the change of base all the time because I'm quicker at just, especially if I'm not doing it on the screen here, if I'm doing it with a handheld calculator, I'm faster at pressing buttons than I am at going through menus and finding things. So a lot of times I use change of base anyway, just because it's faster for me. But again, either of those ways, that's change of base formula. So if you see change of base on the final exam, understand, hey, this is what they're talking about. And actually, I think the one problem that I've seen on the final that does this is actually it doesn't work out the decimal for it. It actually shows you what would this problem be? How would you do this problem using change of base? And it gives you like 4 answer choices that look like this. And you got to pick the right one. Which one is the actual change of base formula? And it's just always log of the big thing on top, log of the base on the bottom. That's the way, base on the bottom is the way I've always remembered it. Base on the bottom. So base on the bottom. That's the way I remember that always. So that gets you the evaluating some logarithms using the calculator. That's going to be helpful here because we're going to talk about an application of this, which is actually it's a whole nother section, but I'm just going to continue it inside of this section. And because there's only really one application that we're going to do inside of this, and then we'll take another break, and then we'll come back and solve some equations. So pH balance, or pH using logs. All right, so pH is equal to the negative log of the concentration of the hydrogen ion is what that's called. It's a little chemistry application of this. This is a carryover from college algebra that they brought into this course. A lot of people that have to have college algebra have to have chemistry for whatever degree you're getting. Not everybody has to have chemistry anymore. This is one of those carryovers from the days when everybody had to take chemistry, which is not the case now. But it is a good application of logs, and we struggle to find applications of them, so we just hung on to this one because it works. Okay, the pH of water. It's summertime. It's pool season. If you've got a chlorine pool, you got to keep the pH. You got to keep a check on it. If you got a saltwater pool, you're supposed to check that anyway, but it really doesn't get as sideways as quickly as a chlorine pool does. So we've got a lot of rain in the last couple of days. My in-laws have a saltwater pool. They don't have to worry about it too much because they keep enough salt in it that if it rains, it's not going to knock off the pH too much. But if it was a chlorine pool, you got to check it because that pH gets too basic or too acidic. Then you start getting things growing in there, or it starts, affecting your skin quite a bit with that chlorine in the pool. So checking the pH. The equation that we're dealing with here is that the pH level of the water is equal to taking the natural log of how much of this hydrogen ion there is in the water. And they sell these testing kits that do all this stuff for you. But if you had the information given to you, and this is they give you a chart at the pool store that has these numbers on it and tells you what it is. So you actually don't have to do this calculation. But if you wanted to, you could now. I don't know if anybody wants to do pool maintenance, but you can actually calculate this stuff for yourself. So let's say we wanted to find the pH when the concentration of H3O, hydrogen ion, is equal to 2.5 times 10 to the negative 4. So there's a scientific notation number thrown in there for us, harking back to days of science fairs and scientific notation. I always think about that. So when you set up that equation here, where they give us the number that's in that log, that it's 2.5 times 10 to the negative 4. We just got to know how to put that into our calculator because all we're asked to do is find the pH. All right. So this one's a little easy. It's evaluating with the calculator. So we just got to know how to type that in. So in the calculator, that's a common log. That's log base 10. So I'm going to type log up to the top so you can see negative log. And then I'm going to put 2.5. And I'm going to use that scientific notation deal. Second, and then the button right above 7 gets me that capital E. And then I'm going to put the negative 4. And that's going to give me the pH of that water. That pH is 3.6. And then here's the good thing. If you don't want to use the E to the negative 4 thing, if you want to do negative log and they do 2.5 times 10 raised to the negative 4, I'm pretty certain I get the same number back. So either way there, I like to use that with the calculator in case it's a larger number. All right, so let's pH. What was that number? 3.6, and let's just go one decimal place because usually that's all you're comparing. 3.6. Okay, let's go to a more difficult problem where they give us the pH and want us to find the concentration of the ion. So this is kind of leading us into the next section that we will cover, and that is if the pH is 7.1, find the concentration of not H2O, but H3O, hydrogen ion. Okay, so finding the concentration of the hydrogen ion. Here's the thing: we have this equation that says pH is equal to the negative log of the concentration of the hydrogen ion out of that. So we know that we can plug in some things we know. We know that 7.1 is the pH. That's -1 times the log of H3O positive ion. What base is that logarithm? Base 10, right? Now this goes back to the link between exponentials and logarithms, okay? That -1's in the way. How can I get rid of that -1? A couple of different ways, but one way is easy, one way is pretty fancy. I like the easy way. Because what's really going on between this -1 and the log is that they're multiplying, right? The opposite of that would be divide. If I divide by -1, that gets rid of that -1 that's over here with this log. So I get -7.1 equals log base 10. Technically, that's x, because we don't know. I'm writing this concentration thing here, but we're just going to call that x, because that's what we're looking for. It's the variable. It's the thing we don't know. Now, how can I use what I know about exponentials to rewrite this? Maybe it'll help if I rewrite it in this order so that it looks a lot like what we've done before. So that's log base 10. So we could take this logarithmic statement and rewrite it as an exponential. 10 to the -7.1 is equal to x. And 10 to the -7.1 I can work out. 10 raised to the -7.1. And I'm going to write that in scientific notation. 7.94 times 10 to the -8. That's our concentration of our hydrogen ion. So it's taking that and rewriting it as an exponential. So it takes what we did earlier and applies it to something here. Not a really hard application of it. It's just got to remember that that's what you've got to do, is just rewrite it as an exponential and then go from there. All right. Evaluating with the calculator is going to be a big part of that particular section. The application with the pH out of that's definitely that has been on the final pretty much every semester for 110. I'll go ahead and say that for sure. The next section that we'll talk about here are going to be solving equations. So let's take a break before we get into that, and then we'll come back and we'll solve some equations, and that'll get us through with all of the stuff for chapter 4 out of this section. So let's take a break. It is 19 minutes till 7. Let's take a let's start back at 7. That's an easy way to remember it, and that gives you time to get a snack or make a phone call if you need to.